Now we're going to take a look at some characteristics of polynomials. So one of the first things we're going to define is what is an even polynomial and what is an odd polynomial. An even polynomial, this is going to be pretty straightforward, but an even polynomial is one that has an even degree. An odd polynomial is one that has an odd degree. Let's take a look at some examples of this on Desmos. So if I graph, I already got one in here. If I graph x squared, we can see it has that parabola shape. If I graph x to the fourth, similarly, anytime I graph an x value with an even power, we can see that it has the characteristics of that U shape. Now, I want to take a look. Let's take a look at this one. If I make both of these squared, this is also still an even polynomial. And even though it has sort of a weird shape to it, let me see if I can, it's got kind of a U shape to it. It still retains, if I ignore the stuff that's going on in the middle, it still retains some sort of a U shape. And if I were to zoom out a lot, and let's see if I can do this, if I were to zoom out a bunch, we can see that it's still, I know it does have this curve in the middle, but it still kind of has that U shape on the edges. This stuff out here is called the end behavior. An odd degree polynomial, one like x cubed, sorry about that, it's late, I'm not doing great with this. X cubed has that S shape, right? We can see that s cubed, same thing if I go x to the fifth, it retains that. I can put any odd degree, x to the 11th, and it will still retain that shape. Now, what we're talking about with regard to this shape is the end behavior of the function. So when we think of an even degree, again, we haven't shifted this at all. Notice that if I go back to Desmos for a second, we can use the idea of shifts of graphs. So something like x plus 3 squared will look like the graph of x squared shifted to the left 3 places. And we can see that here. So end behavior of these even and odd functions is very important. As x tends to infinity, meaning as we go to the right forever, what is happening to the y values? The y values are going to be going up, so the y's are also going to infinity. When we're going to the left, or as x is going to negative infinity, the y values are also going up, so the y's are also going to infinity. Now with an odd degree function, as the x values go to infinity, the y values are going to infinity as well. So as our x's are increasing, our y's are also increasing. But as my x's tend to negative infinity, as my x's go to negative infinity or to the left, we can see that those y values are going down, so the y's will tend to negative infinity. This is going to be an important concept for us to help sketch a graph. Eventually, what we're going to try to get to is, if I give you a graph of any polynomial, we should be able to sketch a graph of that. And we'll try a little bit of this here in a second. A zero of a function is the same thing as an x-intercept. And I know you might be thinking to yourself, why don't we just call them x-intercepts? Well, we're going to think about this in terms of another function. Let's say I have a function, f of x is equal to x squared minus 4. And I'm pretty confident that if I graph this, this is going to look like the graph of x squared shifted down 4 places. And I'm pretty sure that it's going to cross the x-axis at -2 and +2. So we're pretty confident that the zeros of this function, or the x-intercepts, would be at x equals -2 and +2. Now, if I plug that in, if I plug 2 in, I get 2 squared minus 4. I do get a value of 0 out. So we call it a 0 because it is a number that when I input into the function, I get a 0 out. So a 0 of a function is a x value. An example such that when we plug it in, we will get 0 out. So f of a, so if a is a 0, f of a equals equals 0. This is the formal definition of what if 0 is. Let's take a look at this function. This is a polynomial. And I know that this is in factored form, and that's really nice for us, but you might look at this and say, what's the degree of this polynomial? Well, if I think about it, this has a first degree term, and then there are two factors of x minus 3. So it's x minus 3 squared. There are two of those, and then there is a single x plus 2. So the degree of this polynomial is, in fact, 3. We can find that by counting the degree on each of these factored forms. If you don't believe me, another way we could go about this is I went ahead and I FOILed this out, and you can see that this is the polynomial that we would end up with if it was completely expanded. Our constant term would be out here at 18, and we can see that that highest power is in fact a degree of 3. So what is the degree? We just said it was 3. Based on that information, what is the end behavior? One thing we want to make sure we take into consideration on top of the degree is the fact of whether the leading coefficient is positive or negative. Why would we need to do that? Well, if we take a look at a Desmos graph, let me reset this window real quick. If I look at a function like x cubed, I have the traditional end behavior. As x tends to infinity, y goes to infinity. As x goes to negative infinity, y is going to negative infinity. But if I have a negative leading coefficient, that changes that end behavior because I have reflected the graph over the x-axis. So we're going to want to make sure, before we find the end behavior, that we identify what the leading coefficient is. And in this case, we can see that if we FOILed it out, there's no numbers in front of any of these. The leading coefficient of that polynomial would be a positive 1. So based off of that, what is the end behavior? Well, as x goes to infinity, it's going to have the same end behavior as any odd graph. So as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y is, so as we're going over here, the y's values are going to be going down as well. It's really important that we get used to this notation because I will be requiring it. Now, what are the zeros of this polynomial? Well, we've done ourselves some favors here by getting it in the factored form. We know we can find zeros by setting the function equal to 0. So I would set this equal to 0, and then if it's factored, we can set each of these factors equal to 0. So if I do x minus 3 equals 0, I add 3 to both sides, and we get a 0 of 3. I subtract, if I do the other one over here, x plus 2 equals 0, subtract 2, I get x equal to negative 2. So my zeros are going to be x is equal to 3 and x is equal to negative 2. I do have two x minus 3's, but they're going to give me the same number, so I'm not going to write repeats. Let's graph this, and what do we notice about the zeros? All right, so I'm going to zoom out a little bit so we can see a nice picture of this. And we can see that it does have that end behavior. As x goes to infinity, y goes to infinity. As x tends to negative infinity, y tends to negative infinity. Let me shrink this graph a little bit. I'm going to bring this in a little bit so I can zoom in. All right, so I can see my x-intercepts. There's one right here, and there's one right here. But notice that they're kind of doing something differently. At negative 2, the graph is passing through that x-axis. But when I get over here to positive 3, it doesn't pass through the x-axis. It bounces there. And you might ask yourself, why is it passing through over here, and then why is it bouncing over here? Well, let's take a look at the function. So what do we notice here? At x equals negative 2, it passes through the x-axis. And at x equals 3, it bounces. Sometimes they will say it touches, or I like the idea of it bouncing because, again, when you take a look at the graph, you can see it's passing through here, and then when you hit this one of 3, it kind of bounces off and heads back up. So what's the difference between these? Well, when you take a look at our original function, there are two factors of x minus 3. One thing that we will say about this is that that has the 0 of 3 right here would have a multiplicity of 2. And x and negative 2, there's just one of those zeros, so that has a multiplicity of 1. So formally, if a 0 has an even multiplicity, meaning if there are an even number of those zeros, it will bounce at the x-axis. So again, if it's something like here and it's an even multiplicity, it's going to come down and it's going to bounce. That's true for both even and odd functions. Let me give you an example of that. If I have a graph of, let's just delete this, x minus 3 squared, you can see there are two factors of x minus 3. This heads down, it gets to 3, and then rather than passing through, it bounces back up. Graphs that have odd multiplicity, zeros that have odd multiplicity will pass through the x-axis. So again, we saw that with that graph of x minus 2.